Hi everyone, here are solutions for 13.4. We're going to do this set right here, page 870, 12, 15, 16, 28, 40, and 43. All right, here we go, starting with number 12. The question states, find the velocity, acceleration, and speed of a particle with the given position. And the position vector that we're given has x component t squared, y component 2t, and z component natural log of t. So as we've learned, velocity is the derivative of position. And so our derivative would be 2t, 2, and 1 over t. And then our acceleration vector is the derivative of velocity, or the second derivative of position. And so that vector is 2, 0, and then negative 1 over t squared. We're also asked for speed, and speed is the magnitude of velocity. So our speed, we can call that magnitude of r prime of t, or we can call it ds dt. And that would be the square root of 2t squared plus 2 squared plus 1 over t squared. Okay, number 12 is done. Let's look at 15. All right, find the velocity and position vectors of a particle that has the given acceleration and the given initial velocity and position. Okay, so we are given that acceleration is the vector 1, 2, 0. We're also told that the velocity at time t equals 0 is the vector 0, 0, 1, and that the position at time t equals 0 is the vector 1, 0, 0. Okay, so to find velocity, we have to take the integral of acceleration with respect to time. Don't forget your constants. That's what's going to make this quantity right here useful. So this means we'll take the integral of 1 with respect to time. That gets us t, and I'm going to use different constants each time. So I'm going to say t plus c1. Then we've got 2t plus c2, and we have just a constant c3. Now we have to use the fact that v of 0 equals 0, 0, 1. So that when I substitute 0 in for t, I should get out 0, 0, 1. This means that c1 is 0, c2 is 0, right? Because if I substitute 0 in for t, I'm going to get 0 plus something needs to equal 0, and that has to be 0. And then c3 is going to equal 1. So my actual velocity vector is t, 2t, and 1. And now we're going to find the position vector from that. So r of t is the integral of v of t dt. So we've got t squared over 2 plus c4. I'm going to use a different constant each time. T squared plus c5, and then t plus c6. And then here is where we're going to use, sorry, didn't mean to highlight that. We're going to use this quantity right here. So when t is 0, we want the first component to be 1. That means that c4 must be 1. And when t is 0, we want the second component to be 0, so c5 must be 0. Similarly for c6. So our position vector is t squared over 2 plus 1, t squared, and t. And I'll take a moment to check that with the solution manual. Yes, you can laugh at me for doing that if you want. T squared over 2 plus 1, t squared, and t. Yep, got it right. Okay, now we'll do 16. Very similar problem in number 16. Okay, so this one has an acceleration vector of 2, 6t, and 12t squared. Our initial velocity is the vector 1, 0, 0, and our initial position is the vector 0, 1, negative 1. So velocity is the derivative of acceleration. So we'll do component by component. We've got 2t plus a constant. We've got 3t squared plus a constant. And we have 4t cubed plus a constant. Using this fact that the velocity at time t equals 0 is 1, 0, 0, that requires C1 to be 1, C2 to be 0, and C3 to be 0. So our actual velocity vector is 2t plus 1, 3t squared, and 4t cubed. All right, let's integrate that. So position is the antiderivative of velocity. So we have t squared plus t plus a constant. We have t cubed plus a constant. And we have t to the fourth plus a constant. Using the fact that at time t equals 0, the position has to be 0, 1, negative 1, we see that C4 must be 0, C5 must be 1, and C6 must be negative 1. So I have a position function of t squared plus t cubed plus 1, and t to the fourth minus 1. And again, I'll take a peek at the solution manual. T squared plus t cubed plus 1, and t to the fourth minus 1. Yep, all good. Okay, next up is 28. Okay, 28 says a batter hits a baseball 3 feet above the ground toward the center field fence. Initial height is 3 feet, which is 10 feet high and 400 feet from home plate. Okay, so we are looking at 400 feet away, 10 feet high. That's what we're hitting toward. The ball leaves the bat with a speed of 115 feet per second at an angle of 50 degrees above horizontal. Is it a home run? In other words, does the ball clear the fence? Okay, so our x function is v naught cosine theta times t. There is no x naught in this case because we're considering home plate, the origin in terms of x. And y of t equals negative 1/2 gt squared plus v naught sine t. Sorry, v naught sine theta plus h naught. Okay, so we can say x of t is 115 cosine 50 times t, and y of t is, g in this case is 32, so negative 16 t squared plus 115 sine 50 t plus 3. So the question is, when we're 400 feet away from home plate, are we greater than 10 feet off the ground? So I'm going to sub in 400 for x. We'll solve that. And then we will use that t in our other equation to see how high we are at that time. So we'll take 400 divided by 115 times the cosine of, they convert to degrees. Okay, so that's our time. I'm going to store that as t, so 5.41. Now I'm going to take y of that answer, 5.41, and we'll see how high we are after that amount of time. So negative 16 times t squared plus v naught times the sine of theta times t plus 3, and I get that I'm at a height of 11.2. So the answer is yes, we do have a home run because we have cleared the fence. I want to confirm that on the solution manual. Yep, good, it's a home run. Okay, 40. Okay, 40 says find the tangential and normal components of the acceleration vector. If you're one of the people that was asking questions about some of this in class, I do have some things to say about that I've found on Google. I'll share those in class next time, although I don't have a complete derivation of that a.n thing that we were talking about, so we'll have to talk about that a bit more. Okay, so we've got t squared, and 3t. Okay, so if we refer to our formulas for normal component and tangential component, our tangential component is r prime dot r double prime over the magnitude of r prime. Okay, the normal component is the magnitude of r prime crossed r double prime over the magnitude of r prime. I think I'll do this one completely on calculator just to avoid some of the tedious work. I'll just show you the commands that are on there. So let's define r of t. Oh wait, I can't use t because it's defined elsewhere. Okay, so define r of t to be the vector function, sorry, let's go back, t squared, and 3t. So for our tangential component, we're going to take the dot product of the first derivative of r of t and the second derivative of r of t. We'll divide that by the magnitude of the derivative squared. Okay, so my claim is that tangential component of acceleration is that component. There's that expression. Let's see if I'm right. 4t, that's not what I have in the solution manual. So let's see if I did something wrong here. Unless it's equivalent forms, it could be equivalent forms. I don't think it is. Okay, let's see what I did wrong. First of all, is r of t defined properly? R of t is t squared, and 3t. No problems there. Oh, I see the problem. It's not squared in the denominator. Now I think it's right. Is it still wrong? Shoot, it's still wrong. No, I think I have equivalent form. Let's see. The solution manual says 4t over square root of 4t squared plus 10. Factor out a 2. I still don't think it's the same. Got to reconcile this in my head. Let's see. Sorry, you can, of course, skip over this part of the video if you want. All right, so I'm showing that this is a sub t, and the text is showing that the answer is 4t over the square root of 4t squared plus 10. Okay, so I could write this as 4t over root 2 times 2t squared plus 5. So I could say that that's 4t over root 2 times root 2t squared plus 5. And then multiply top and bottom by root 2. Would get us 4t root 2 over 2 times root 2 squared plus 5. So we do have equivalent answers. Okay, good. And then a sub n, normal component of acceleration, will be same process. So let's just redefine. Let's just take this and change this to cross product instead of dot product. And we have the magnitude of that. Let's change it here. So we want the magnitude of the cross product. There we go. And that is equivalent to the answer in the solution manual. Okay, if I have another problem assigned from this set, let's just skip it. 43, what did I choose? No, 43 is actually a good one. Let's look at it. Okay, in 43, we're given a sketch. The magnitude of the acceleration vector A is 10 centimeters per second squared. So the sketch looks like this. The curve is going like that, and you've got an acceleration vector pointed like that. And we're supposed to estimate the tangential and normal components of A. Okay, so the question is, if we resolve this into like a quantity in the direction of motion and a quantity in the orthogonal to the direction of motion, we're supposed to estimate what those are. So this thing has a magnitude of 10 centimeters per second squared. This angle here looks a bit more than 60, maybe about 60, which would mean maybe tangential component would be about 5 and normal component would be about 5 root 3. That's just, but again, it's just an estimate. So you could say that A equals 5 times big T plus 5 root 3 times big N. Maybe it's a little bit stretched from that, but that's all you're being asked to do is just estimate. Okay, we can discuss in class if needed. Thanks for watching.